All right, what's going on, you guys? Welcome to another video on prime logic. Today I've got a really interesting, mind-blowing, kind of mind-boggling problem for you today. So if you want to solve this problem, please pause the video because I'm going to solve this problem right now. So let's review the assumptions of this nasty-looking problem. So a lot of students, I think, would feel scared of this type of geometry problems, but I think once you crack the code, you can solve almost all of them relatively easily. So we have a big square here whose side is 6. So divided by 3 little squares on each side. So in total, this whole square is comprised of 9 little squares with a side of 2 each. And this shaded area, which is green, which I colored that in green, it is bounded by 4 quarter circles. So we have according to the question, we have a 1/4 circle here, which goes from this vertex of this square to the other vertex. So this big thing here, it is a quarter circle. So imagine this is a whole circle, a big circle, but this is just a quarter circle. Another one, here we have another quarter circle from this side to that side with a radius of 4. We have another quarter circle similar to this one from this side to that side with a radius of 4 again. And we have this little quarter circle here with a radius of 4. These 4 quarter circles, they bound an area. So this bounded area, which is colored in green, that's a point of focus in our problem today. So the first approach, I'm going to give you 2 approaches, 2 methods. One of them is the line approach for those of you who just want to follow an orthodox, kind of conventional step-by-step guide. And there is also a very, very short and simple but intuitive way. So for those of you who just want to follow their intuition, I think the second approach is more apt and suitable. So let's start with the first one. So the area of the green area, the shaded area, is equals to the area of the big square minus this white area, this unshaded area. So if we can find a way to calculate the area of this white areas or unshaded areas, we can find the area of this green part. So we know that this part is 4 because it is 2 divided by 2. That's in a square here. That's another one 4. This is this is a diagonal line here. That's a right angle isosceles triangle here. So the area is 2 times 2 divided by 2. So 4 divided by 2 is 2. Let's go now for this red area here. So which starts from here up to here. So this red area, we can say that this red area, if we subtract the area of this big quarter circle from this whole big square, so what we have is the area of this red part here. So let's write it down. The area of this red part is the area of a square. So let me write it down here. So that's going to be the area of a square, which is 6 times 6, 36, minus the area of this quarter circle. So let me write down the formula for the area of the quarter circle. So pi r squared over 4, that's the area of a quarter circle. So 36 minus the area of the quarter circle, pi r squared, which is 6 squared, that's 36 over 4, which is 9. So it equals to 36 minus 9 pi. So that's, so let me write it down here. That's 36 minus 9 pi. So that's the area of this red shaded area. And the same goes with this part as well. So we also need to find and calculate this area. So this area equals to the area of this square, which is a 4 by 4 square minus the area of this quarter circle, right? So if we subtract the area of the quarter circle from this biggest square, what we have left is the area which is colored red here. So let me write it down here again. So 4, the area of the square, 4 times 4, that's going to be 16 minus pi r squared. So r in this case is 4, squared is 16 over 4. So it equals to 16 minus 4 pi. So let me write it down here, 16 minus 4 pi. So other steps include finding these areas as well. So let me extend this diagonal line a little bit here so that we know what we're going to solve and find here. So the next step is to find this. Let me color that again in red, maybe. Okay, so this, okay, I don't color that because we'll have something to do with it in the next part of this video. So the next part is finding this area of this part. So this is not a circle or quarter circle anymore. This is a segment, right? So this is because this diagonal line, it's not the diameter of this curvature, this curve here, which is a quarter circle. So this big thing here, yes, this is a quarter circle. We know the area of this quarter circle here, and if we subtract this right-angled isosceles triangle, what we have here is this area of this segment, because this is just a chord for this circle. This is not a diameter. So let me write it down now. The area of this quarter circle is pi r squared. So r in this case is 4. 4 squared is 16 divided by 4, which is just 4 pi. So pi r squared, this is the area of this quarter circle, minus the area of this isosceles right-angled triangle. So the sides are 4. So it is 4 times 4 over 2. So this becomes, this is just 4 pi, and this thing here is 8. So this big area here is 4 pi minus 8, this thing here. So let me maybe put it here, 4 pi minus 8. Let's go with the same approach with this part. So we can see that we know that this part is also a quarter circle. And if we subtract the area of this right-angled triangle, what we have here is the area of this segment which is bounded by this chord. So pay attention, this is not a diameter of the circle, this is just a chord of the circle. So let's write it down again. So pi r squared, that's the area of this big quarter circle. The radius is 2, so 2 squared is 4 over 4, because that's a quarter circle, minus the area of this right angle isosceles triangle. So 2 times 2, 4 divided by 2 again. So that's going to be pi minus 2. And this area, little area here is, let me write it down here, pi minus 2. And it is also 4 pi minus 8. So voila, we found everything. We found everything that was bounded by this unshaded area. So we found anything other than this green area. The rest is just algebra. That's a bunch of integers and pi. So let's write it down here. This whole biggest square was, write it down here, it was 6 times 6, which is 36, minus this whole white area, or just maybe a red area. So let's add everything together. So we know that 4, so we have the 4 here, plus another 4, plus 2. So these three shapes here, and then we have our curves here. So the first one was plus 36 minus 36 minus 9 pi. Another one was 16 plus 16 minus 4 pi. Another one was 4 pi minus 8. And the last one was plus pi minus 2, right? So this is just algebra. This is the area of green area, let's say. So let's just add them together. So it's going to be 10, this part, right? So 10 plus 36, 46, 56, 62, 62, I think, minus 10, that's going to be 52, I think. Yep, so 36 minus 52. So let me just add it together. 10, 46, 62 minus 10, yes, 52. And then we have a lot of pi's here. So the first pi is minus 9 pi, minus 4 pi, minus 13. Oh, okay, so we have two minus 4 pi's and plus 4 pi. So that's going to be minus 8 pi. So 52 minus 8 pi, which equals to 36 minus 52 plus 8 pi. So the final answer is 8 pi. 36 minus 52 is minus 16. So that's our answer, 8 pi minus 16. So obviously square something, square units. So the first approach was finding the area of this biggest square and then subtract this area of this unshaded area, or white area from that. What we have left is the area of this green part, this bounded green area. Okay, so that was the first row. Let me wipe out this. The whiteboard here now, so just a moment, please. Okay, great. So for those of you who are waiting for this second kind of intuitive method, which makes it way easier. By the way, I'm sure this is not the only way, because most of the time, almost always in geometry, so there is n times, n methods possible, countless methods possible. So please write me in the comments below your methods, how you would approach this problem. So we have this diagonal line here, right? So for this intuitive approach, which kind of challenges your spatial geometry, so it is just something that maybe a lot of students wouldn't imagine. It improves your imagination, I think, if you think this way, and it needs a lot of imagination, and you need to envisage a lot of like shapes in your mind. So let's draw this line here. So what if I tell you, so I think by now you know that this curve here, which is a quarter circle with a radius of 4, it's the same thing as here, as this quarter circle with a radius of 4. It means that they are just the same, but they are drawn on the other side. So they are just 100% congruent. They can be overlaid on one another. So what if I tell you we can grab this part here, just this part above this diagonal part, and then just map it or teleport it to this side. So what we have left, so sorry, I'm going to write it, I'm going to draw that by hand, but we have something like this. So this part will be teleported to this part, and that was cool, I think. What do you think? So this here, which I'm going to shade it by, again, red here, it's exactly the same thing as here. So the area, this green area equals, now this is a new green area here. So that's going to be this green area plus this area. So this is our transform shape. So this shape, if we can find this part, which is a big segment of the circle, then we subtract this from there. That's okay, our answer. So we have a segment minus another segment. So this is a segment, this is also another segment. So let's see how fast we can solve this part. So the area of this segment is the area of this big quarter circle, which is going to be pi r squared. R is 6 squared, 36 over 4, which is 9 pi, and minus the area of this right angle isosceles triangle, which is 6 times 6, 36 over 2. So 36 over 2, that's 18. So 9 pi minus 18. That's the area of this big segment, including this part. So this big part here. Now what we're going to do is to reduce or subtract this segment as well from this one. So the segment here is the area of this quarter circle. First, this quarter circle, which is pi r squared. R is 2 squared 4 over 4. So this is going to be just pi minus the area of this right angle isosceles triangle. So 2 times 2, 4 divided by 2, 2. So it's going to be pi minus 2. And that's it. So let's subtract them, this one from that one. So 9 pi minus 18 minus pi plus 2. And the answer is 8 pi minus 16, which is the same as our previous answer, and that was just 3 lines. So, but that was more intuitive, way more intuitive. I'm sure a lot of people, a lot of students, so they wouldn't think about it at first glance, because you need to kind of teleport it, because these shapes are symmetrical to the other side. Now I have a couple of challenge, not challenge, but maybe, yeah, one of them is a challenge. So first is, I really look forward to seeing your solution. So obviously I'm sure that these are not the only solution. I'm sure there is a ton of other solutions as well. And I always learn from you guys in the comments below. So make sure to put your solutions down in the comments below. And another maybe challenge or a question for you. So the question told us that these curves here are quarter circles. So it means that they are spherical, so they are part of a circle, right? That's why we could use this quarter circle formula. But what if they were not part of a circle? They were just a spherical, not a spherical. So how would you solve this? Would it be possible? What parameters do we need to consider? Or maybe it is not possible, it is impossible to solve that at all. So I think that's going to wrap it up for today. I think that was a really interesting, mind-bending geometry problem that I really liked as well. And so make sure to subscribe if you haven't already, and like, share, and comment, and drop your thoughts in the comments below. And as always, I love you guys, I appreciate you guys, and see you in our next video on your channel, Prime Logic.